Okay, Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. We have come to the last part of topic 2, which is on buoyancy. So these are the references that you can go through to understand more about fluid mechanics. And this is the overview of what we will learn today, which is on buoyancy from Archimedes' principles. At the end of this lecture, you should be able to formulate and apply buoyancy principles of fully submerged and floating bodies to solve problems. Okay, I hope that you still remember what we have learned previously in physics. Archimedes' principles state that for a body completely or partially immersed in liquid, the upward buoyant force acting on the body is equal to the weight of the liquid it displaces, where this can be simplified by this equation. Buoyant force is equal to the weight of liquid displaced. So Fb is equal to rho GVD, where this is the density of liquid, this is the gravitational accelerations, and Vd is the volume of fluid displaced. Okay, let's look at this figure. What will happen when the weight is much lesser than the buoyant force? The object will rise in water. When the weight is much bigger compared to the buoyant force, the object will sink to the bottom. And when the weight and buoyant force is equivalent, is equal, so the object will float, yeah, in water. Conditions of equilibrium of a floating and submerged bodies. So we have three: the positive buoyancy, where the buoyant force is greater than the weight, so the object will float. Secondly, the neutral buoyancy, where the buoyant force is equal to the weight, so the object is suspended in the liquid. And the negative buoyancy, where the buoyant force is less than the weight, so the object will sink to the bottom. Principle of buoyancy. So buoyancy is the vertical force exerted by the fluid on an immersed body. Center of buoyancy, CB, is the point in which buoyancy is acting and the centroid of the displaced volume of fluid. And buoyancy is the weight of fluid displaced by the body. So we know that Fb is equal to rho g Vd. So rho g can be replaced by gamma. So gamma is the specific weight of liquid obtained by multiplying the density with the gravitational accelerations. Vd is the displaced volume of liquid in meter cube. So procedure for solving buoyancy problem. First of all, we have to draw the free body diagram to identify the vertical forces acting on the object, which is the weight and the buoyant force. Then we have to write the vertical equilibrium equation. Summations of Fv must be equal to 0 so that it will not move. Solve for the required by applying buoyancy principles. So we have the equations for buoyant force. Fb is equal to gamma Vd. Weight of object is equal to gamma V object. Depth of immersions or submerged depth x can be obtained by dividing the Vd with surface area. Yeah. So Vd is the displaced volume of water. V object is the volume of object. A is the base area of object. So this is the illustrations of buoyancy. Yeah. So we have apparent versus real weight. So force apparent is equal to a weight minus buoyant force. For example, when we hang this ground uh, on air, so we got the weight as 14.7 kilogram. However, when we immerse this in water, so the weight turned out to be 13.4 kilogram. So what happened is actually the buoyant force make the apparent weight to be 13.4 instead of 14.7 kilogram. So mass of displaced water is equal to 14.7 minus 13.4. We got it as 1.3 kilogram. So we can obtain the volume of displaced water as this. Example, a stone weighs 665 Newton in the air. When the stone is completely submerged in water, it weighs 420 Newton. So where does the weight goes? The buoyant force, which force it upwards. Calculate the volume of the stone. The unit weight of the stone is 9803 Newton per meter cube. So we got the weight actual as 665 Newton and apparent weight as 420 Newton. So we actually know that the buoyant force is 665 minus 420, which is 245 Newton. So this is the buoyant force. How can we calculate the volume of the stone? We know that FB is equal to W and W is equal to rho g V naught. Why V naught? Because it is completely submerged. So the overall volume of object displaced the water. Yeah. So next, by dividing this, we can obtain the volume of the stone to be 0.025 meter cube. Okay, let's proceed. You should be able to evaluate the stability of a floating and fully submerged body and define the metacenter and metacentric height. When a body floats in vertical equilibrium in a liquid, the buoyant force will act through the center of buoyancy, and the weight of body will act through the centroid or the center of gravity. For equilibrium, both buoyant force and weight must be equal and act in the same straight line. The equilibrium of a body may be stable, unstable, or neutral depending upon whether when given a small displacement, it tends to return to the equilibrium positions, move further from it, or remain in the displaced position. So let's look at this figure. The weight of object W will act through the center of gravity of the object, whereas the buoyant force Fb will act through the center of buoyancy Cb. For fully immersed object, the shape of the displaced fluid is not altered when the object is tilted, and so the center of buoyancy remains unchanged relative to the object. So when we look at this figure, we can say that uh, the overturning moment will cause the object to return to the original position. So it is stable. When there is a small angular displacement theta, moment will be generated. Hence, if the center of gravity Cg is below the center of buoyancy, this will be a righting moment, and the body will tend to return to its equilibrium position. However, if the center of gravity is above the center of buoyancy, an overturning moment is produced and the body is unstable. Let's look at this. So it will turn upside down. So it is unstable. So the center of gravity must be lower than the center of buoyancy for it to become stable. If the center of gravity is located higher than center of buoyancy, then the object will overturn. Okay, let's move on to the metacenter and metacentric height. Metacenter MC is the point at which the line of action of the upthrust cut the original vertical through the center of gravity of the body center of gravity. So X is equal to mb times theta, provided that the angle of tilt theta is small, so that sine theta is equal to tangent theta, which is equal to the theta in unit radians. The point MC, your metacenter, is called the metacenter, and the distance MB is the metacentric height. It is measured from the center of buoyancy to the metacenter. So MB is the distance from center of buoyancy to the metacenter. And we can obtain the value of MB by using these equations, I over VD. So I here is the second moment of area of horizontal sections of the body and the surface of the body. and Vd is the displaced volume of liquid in meter cube. So let's compare figure B and C. If MC lies above CG at the centers lies above center of gravity, a righting moment is produced, so equilibrium is stable and MB is regarded as positive. However, if MC lies below the CG, an overturning moment is produced, equilibrium becomes unstable, and MB is regarded as negative. For the case of D, if MC coincides with CG, then the body is in neutral equilibrium. So checking for stability. So this is the theory, you can read this, and this is the application. So easily to see, when the YMC is greater than YCG, the object is said to be stable. When YMC is less than YCG, it is unstable. And when YMC is equal to YCG, it is neutral equilibrium. Okay, so this is the scenario that we had just talked about. Procedures for determining stability of floating bodies. So first of all, we need to determine the position of floating bodies using the buoyancy principles. Locate the center of buoyancy and calculate the distance from the bottom of body to center of buoyancy, which is known as YCB. Locate the center of gravity and calculate the distance from the bottom of body to CG, which is known as YCG. Calculate the second moment of area I of the plane cut by the water surface, hence calculate the MB. Calculate the distance from the bottom of the body to MB using this equation to determine the value for YMC. Meaning that first of all, you have to determine the value for YCB, then the value for YCG, then the value for MB. You add up these two, you get it as YMC. Then you have to compare it with YCG. So remember this equation. If YMC is bigger than YCG, it is stable. If not, it is unstable. Okay, example. A flatboat hull weighs 130 kilonewton when fully loaded. Determine whether the boat is stable in water and find out if the boat will float. The center of gravity is at 0.7 meter measured from the bottom of the boat. The length of the boat is 6 meter, the width is 2.2 meter, and the height is 1.2 meter. Okay, what we can do, first of all, we use the equations FB is equal to weight of object. So FB is equal to rho GVD. So from here, we got X to be 1 meter, depth of immersions. So VD is 13.2 meter cube. From there, we can determine the center of buoyancy. So YCB is equal to X over 2. So it is 0.5 meter from the bottom. And the center of gravity is 0.7 meter, which is given in the questions. So from there, we determine the value for I. Remember, I is the second moment of area of the plane cut by the water surface. So the way we calculate I is that we have to look it from the plan view. So I would be LB cubed over 12. So length is 6 meter and B is 2.2 meter to the power of 3 over 12. We got it as 5.324 meter. Determine the value for MB, I over V as 0.4 meter. And then we can determine the value for YMC, which is YCB plus MB. We got it to be 0.9 meter. Remember, we have to compare the value for YMC with the YCG. If the YMC is greater than or equal to the YCG, the body is said to be stable. So in this case, the boat, the flat boat hull will stable and will not overturn. Okay, so that's all. Thank you very much. Please go through the slide that I have shared in your future for better understanding and more examples related to buoyancy. Thank you very much.